Hi everybody, I guess you can hear me. Thank you for attending this presentation. Today I will talk about transpilers in the context of legacy system modernization, also known as reengineering. But first, I will introduce myself. So my name is Lorenzo Addazi, that's a picture of me some years ago, and I work as a software language engineer at Strumenta, which means tools in Latin. We are specialized in language engineering services, so we generally build domain-specific languages, compilers, interpreters, static analysis tools, and lots of other things. So what are we going to talk about today in detail? So we are going to start introducing legacy systems, so what they are, and why can this be problematic for businesses, and how to cope with these problems. Then we will introduce the concept of legacy modernization, and how legacy systems can be re-engineered in order to use modern technologies while limiting risks and costs. So in this context, we'll talk about transpilers and how this can be used to implement legacy modernization in a kind of semi-automated manner. And finally, we'll take a look at an example transpiler translating RPG code into Python. So what are legacy systems? Over the past decades, numerous companies, as we know, have adopted software systems to implement critical tasks of their business. While many of these systems have been constantly replaced with the evolution of business needs and new technologies, some of them are still alive, and we call them legacy systems. There exist a lot of definitions for what a legacy system is, and one I like the most is taken from the good old book Software Engineering by Somerville. And legacy systems are defined as older systems that rely on languages and technologies that are no longer used for new system development. So they're old. Okay, good. But what is the problem with legacy systems? The main problem is that they are hard and especially expensive to maintain. Why? There are many reasons. The first, probably the most known, is that when you have obsolete programming languages and technologies, it's very difficult to find people that have knowledge and or interest to work with this. So most of the times you need to use expensive outsourcing. So pay a lot of money to another company to maintain this software. Another problem is the code, especially software maintenance involves understanding the program that has to be changed and actually implementing the change. But legacy systems tend to be difficult to understand for various reasons. Oftentimes the program style and the usage conventions might be inconsistent because a lot of different people have been responsible for the system changes in time. And so these problems add to the usual difficulty that we have in understanding the code that somebody else has written. Also, the system may have been optimized for memory usage or execution speed. So that in order to run in an effective way on limited hardware, old limited hardware. And this translates to probably using some machine and language specific optimizations, which usually lead to software that is really hard to understand. So programmers that have learned modern software engineering techniques and practices often don't understand the programming tricks that have been used. So they have a lot of problems in understanding what the code is actually doing. Also about the architecture of legacy systems is a problem. Many years of maintenance usually tends to degrade the system architecture, and it's increasingly difficult to understand the initial design. Oftentimes, many programs have been added and integrated into the system, so patch after patch, the structure has degraded. About the documentation is often inadequate or out of date, hasn't been updated, and many times, actually the only available documentation is the source code itself. So what I like to call the codocumentation, which it's not a consequence of like maybe some agile believer or practitioner working in the project, but just as it is. So this is a problem also considering the fact that, as I said, the structure is probably degraded patch after patch. So having just the code as documentation is really not a good thing. There are also other problems. Interoperability. Oftentimes, legacy systems might be problematic to interface with our systems that are newer and developed using modern programming languages and technologies. For example, let's say we want to integrate a legacy system and interact with it using some web services. It might not be possible. Also, the support tools that we have can give us problems. Compilers, the debuggers, the development environments that we usually use to develop and that were used to develop the legacy system might be no longer maintained or might require some very expensive licenses. The hardware that was initially targeted by the legacy system is probably obsolete and increasingly expensive to maintain. Think about mainframe computers, for example. So we have a lot of problems with legacy systems. And so a question that might come to us is why just not replacing all of them? A very simple answer to this question is that it's very expensive and very risky to do so. And so if a legacy system works effectively, the replacement costs may exceed the savings that coming from the reduced support costs of a new system. So just replacing the legacy system might open up the possibility of things going wrong and the new system failing to meet the business needs. So managers, of course, they always try to minimize these risks and often do not want to face these kind of uncertainties given by new software systems. They just avoid doing so. But why are they so risky to replace and expensive to replace? Well, in a similar way as they are expensive to maintain, whenever trying to replace a legacy system, the first problem that might come is the documentation. It's incomplete. It probably may have been lost. And if it exists, it is unlikely that it has been updated with all the system changes in time. So therefore, there is no straightforward way of specifying a new system that is functionally identical to the system in use. Also, with the legacy system, a legacy system is often defined as some kind of socio-technical system, which means that it's not just the software, but it's also the business that is around the software itself. So the business processes of the company using the legacy systems are often intertwined with the software itself, which means that they have been defined in a way to use the features provided by the legacy system and to avoid the problems or the shortcomings of this legacy system. So replacing it would also require a review of the business process, which is something that it has unpredictable costs and consequences. And also, this is somehow related to the documentation. It's pretty often in legacy code. There are oftentimes very important business rules that are at the core of the legacy systems, are embedded in the software and are not documented elsewhere. So it might be missed during the replacement of the functionally equivalent system, and breaking this constraint for the company replacing the system could lead to very critical incidents. And with all of this, it's also the typical development risks and costs. So there may be unexpected problems in the development of a new system and may not be delivered in time, or the price might be much higher than expected. So what do we do if we have a legacy system? We cannot replace it, but we still have to somehow handle it. So in order to make legacy software systems easier to maintain, we can do something called reengineering. So, which means that to re-engineer the system in order to improve the structure and the understandability, with the idea of then maintaining it and using some newer technology and just at least making it easier to understand and interact with. So re-engineering typically involves redocumenting the system, refactoring the architecture, translating the programs, the code to modern programming languages and technologies, modifying and updating the structure and the values of the data that's used by the system. But the main difference with respect to a very important fact in re-engineering is that usually the functionality of the software is not changed. And usually, even though we might review the architecture, we're not really applying major changes to the architecture. Which means that most of the times we can perform this process in an automated manner. And the main advantages with respect to replacing legacy systems of re-engineering those is that we have reduced risks and reduced costs. And the extent of such advantages is directly proportional to the amount of automation that is involved, that we succeed in involving in the process. So in this picture, we can see the general process of re-engineering a legacy system. This process model is taken also from the software engineering book by Somerville, more or less. So the input of the process is the original legacy program with its data, and the output of the process is an improved and restructured version of the same program and its data. Not all of the steps are always required, and then it depends on the specific use case. So the first step consists in translating the code, source code translation. So we take the old programming languages and technologies, and we migrate them to some more modern versions of the same or to different ones. This phase is not required if we are targeting the same language or same technologies, but it's kind of hard in legacy systems. Then the following phase is reverse engineering. And during this phase, we analyze the program that we have translated, and we try to extract some information from it. And this is usually helpful to extract the documentation and understand the functionalities. So for example, we might take the generated code and maybe extract some UML class and activity diagrams to have like a vision of the structure and the behavior of the system. And the output is the program documentation. Also, there is the program structure improvement phase, where we analyze the control structure of the program, and we modify it in order to make it easier to read and understand the system. This phase might require some manual intervention. In semi-automated approaches, usually this means defining some patterns that we want to query the representation of the code that we have and apply some changes. So given the program documentation and the restructured program that we obtained from the program structure improvement phase, we go to the program modularization. We try to group together those related parts of the system and remove unnecessary repetitions in the software. In this phase, we might apply some minor architectural refactorings. So similarly to program structure improvement, it might require some manual intervention in general. The output consists of the re-engineered program. So now we have the program. We just need to re-engineer the data. Of course, if we have some data. So during the re-engineering, the data re-engineering phase, we have the original data, and usually, let's think about database schemas or the data itself that is contained in some database. And we just migrate it to some other technology. And this is actually a micro re-engineering process within the re-engineering process. So the same technologies that we can use to migrate source code can be readapted to migrate data. And the output of this phase is the re-engineered version of the original data we had. So what if we want to implement this process in practice? So if we take a closer look at the process, we can see that it's kind of a pipeline. And in that instrument, we call it language processing pipeline. And each component is a language processing component that's taking some sort of the representation of the input code, which might be the text or some tree-like data structure. And we produce a different representation of the same program meant a program, like, let's say, the same semantics. So we do not change the semantics, but we change maybe the view that we want to underline. So it's a pipeline of components. And in this presentation, we're going to focus on source code translation, but similar approaches can be used for program structure improvement, program modularization, and all the other phases of the process. So source code translation can be implemented using a transpiler. What is a transpiler? A transpiler is a language processing component, taking the source code of a program written in some programming language as input, and producing a semantically equivalent source code in a different version of the same language or to a different language and with different technologies. The transpiler preserves it might preserve the original structure of the program or perform some automated refactorings to fill possible semantic gaps between the source and the target language, or maybe different coding practices that exist among the languages. So in this picture, there is a very high level typical architecture of a transpiler as a pipeline. So it consists of 4 phases generally, and as I said before, these are not directly implemented on the text, so the code, but on a tree-like representation that's usually called abstract syntax tree or AST, because that makes all the phases of the process easier to implement and to maintain. So as I said, there are 4 phases. We start with parsing, then we do, which is also known as static analysis, syntactic analysis, and then we have a semantic analysis phase, and transformations, and finally code generation. So during parsing, which is probably the most known phase of this process, we take the text, we group the characters into tokens, and then the tokens into some groups, and from this phase we obtain something called the parse tree, or a parse tree. And from the parse tree we can generate an abstract syntax tree. Generally, the difference is that a parse tree also contains information like commas, parentheses, whereas abstract syntax trees might exclude this information or reorganize the information. Parsers can be implemented using some parser generators. We often use Antler, for example, but can also be implemented manually. So once we obtain the abstract syntax tree of the original language, we oftentimes want to integrate some information that's not possible to express through like a grammar, for example, if we use a parser generator. So for example, it's here that we perform symbol resolution, which essentially means that we connect some sort of runtime object containing all the information that concerns a textual name. So if we are referring to a variable during the parsing stage, we just know that's a name, and with symbol resolution, we just look throughout the AST and we try to link this text to the actual symbol. And another step is type calculation, which is kind of intertwined with symbol resolution, because of course you might need the information about what a symbol is to compute types, but generally It's implemented navigating the AST and trying to infer the type of all the expressions in the code, considering the language specification that we're translating. Okay, so now we have an AST that represents the source program that contains some semantic information. So we are kind of ready to, we know everything we need. Well, there could be some other semantic information we might want to integrate, like maybe track the execution flow, data locality. These are all steps we might have in the semantic analysis. But then we reach the intermediate model. And so we reach a step that it's not really easy to see from the picture, but can consist in multiple transformations. This is where we transform the AST from the source code, from the source program, from the source AST to the target AST. It might consist in many transformations depending on the semantic gap between the languages. And so the semantic information can be used, for example, to understand what to generate in the target AST. So if we think about binary operators, we might have different nodes with respect to different types of the operators. Then we reach the point of having an AST target, the AST of the in the target language, and we generate code from it. So the reason why we like to call it language processing pipeline is that all these steps can be independent components. We have an input and output, and at Strumenta we often have like the single components and then these pipeline compositions that allow us to be much more productive. So let's see a demo of the Transpiler. Okay. So on the left, you can see a Fibonacci, an RPG implementation of Fibonacci. The RPG programming language comes from, the first version is from 1959. This specific code, as you can see, it has fixed column. So the actual column you're writing is a character counts. Some following versions of RPG, they actually relaxed this constraint. But yeah, so we define this very simple algorithm, and so the entry point is actually what we usually call the main. And we are just invoking the Fibonacci, we are just getting the Fibonacci value, giving as a 10 as an input. In this test, we can see the various phases that this specific transpiler has. This is an excerpt of a real project that unfortunately I cannot show you in too much detail. But as you can see, so we start parsing the code, the input code. And here we get the AST. We perform symbol resolution. So we don't have specific explicit type computation in this case to make it simpler. But right after the resolved variable will contain the same AST as the one contained in the result, but with all the symbols resolved. And the result.root that you see it's to say that we are passing the root of the AST. Then we transform the RPG AST that we have to Python. We have an open source component where we define a Python AST and all the code generation support. And by the way, this is Kotlin, so not very popular here maybe. But so we get the Python AST and we generate the code from it. And in this test case, I just wanted to show that, I mean, there are many ways you could translate RPG to Python. In this case, what we do is that we have a class representing the file. The init, initialization logic, we have a reference to the context and all the different variables that we have here at the beginning. The context is usually something when you generate the code, not all the things might be easy to implement, to translate. So you might use some external code that's called the runtime. where you mimic what was, for example, built-in libraries of RPG using Python. And that can be done manually. So it's kind of a way out when things get too complicated. And we have it in the context in this case. So for example, this is what we are doing to translate some built-in functions that are converting a number to a character. So here we're just invoking char, and this is supposed to call a runtime library. Yeah, let's, of course, if we run this test, we can see that it works. Hopefully, yes. Time out. Time is over. So it was a very, very brief demo because of time constraints. So what have we learned today? That legacy systems are bad and can, well, not all the times, but might be problematic to deal with. We've seen that replacing them is not always an option, but rather we can re-engineer those to limit the risks and the cost. So we introduced the general architecture, high-level architecture of transpilers. Now this can be used to perform legacy modernization in somehow, say, an automated manner. And we have shown an example of a transpiler from RPG to Python. So questions are welcome. And one last thing, we're looking for people. So if you might be interested in this kind of stuff, scan the QR code, and we'll be happy to talk with you. And also, we have a language engineering community. You should join us. We always talk about language engineering topics in general, and yeah, all the other social. Thanks.
We have 3 questions. So first one, maybe more, very, very modern. ChatGPT is getting better and better in converting code from language to language. What do you think about using it instead of writing your own transpiler?
We are playing a lot with ChatGPT, but generally generative AI and transformers, like trying to understand how to, this word embeddings, how to represent code and ASTs. So it's promising. But we don't know. Like, we don't know if it's going to be better, especially if you start having specific frameworks to convert. So, but it's of course something to take into consideration.
Okay, next question. Transpile, is it related to DSL, domain-specific language?
Well, no, not necessarily. Like, for example, RPG. It's not really. It's a general purpose language to some extent. So in this case, we're not transpiling to get out from a DSL or to compile a DSL, but we're actually migrating. So, but it could be, yeah. Like we have a DSL and we generate Java code. That's like very common. That TypeScript, for example, is transpiled.
The source code will be abandoned, so the target language will be the new one with the old business logic, is it?
Yes, hopefully.
And last one, what about licensing of source code architecture on a reverse engineering approach?
I'm sorry, can
What about licensing of source code architecture on a reverse engineering approach? I don't know if...
this is, yeah, okay. This is generally a process that you perform with the company owning the code. So they're okay, they're fine with you reverse engineering the code, and it's not like the typical reverse engineering that you might do to, like, for example, like get out of the license limit, but it's just analyzing the code. So, but if you do it, if you take the code of some other, you need access to the source code. So it's not like the typical reverse engineering you might think, like trying to understand the structure of like Word or PowerPoint.
It's basically like white hat reverse engineering.
Yes,
like
yes.
You get paid to do reverse engineering.
Yes.
Okay, if we don't have any other questions, so let me refresh the Slido. I think we are done. Yep, thank you.